In previous video, we have seen point operators. So we know that point operators will work on each pixel at a time. It is vice versa. Unlike point operators, linear filtering looks at small neighborhood around each pixel. Okay, we can consider our image as a collection of pixels. An image is a collection of pixels. So linear filtering apply by considering the small neighborhoods around each pixels. So the point operator can be used to enhance the brightness, contrast, as well as hue or saturation. Linear filtering can be used to enhance image by smoothing, sharpening details, enhance edges, as well as reducing the noise. So next one is convolution. Okay, neighborhood operator means it will uses the value of nearby pixels to design every pixel's new value. The important concept of linear filtering is convolution. Without convolution, the linear filtering cannot be happen. So we'll have a matrix, which is nothing but a kernel in case of convolution operation. We'll apply the kernel matrix over the image and we will compute the weighted sum. Okay, so let us see an example for convolution operation. Okay, example for convolution. I'm just going to have a random value 30, 40, 50, 60, 70, 80, and 90. So this is my image with pixels considered as 3 cross 3 matrix. I'm going to have a kernel matrix, maybe 1, 1, 1, 1. Okay, for simplicity, I'm taking all 1. Okay, how convolution operation takes place means I have to multiply all the values with the kernel values. So this entire image is applied with the kernel. So 10 into 1 plus 20 into 1 plus 30 into 1 plus 40 into 1 plus 50 into 1 plus 60 into 1 and so on. It goes like this. So in real time the kernel value may vary, depends on the types of the kernel. There will be different types of kernels. So based on the kernel the values will be changed. So the result will be 10 plus 20 plus 30 plus 40 plus 50 plus 60, 70 plus 80 plus 90. So this is a very simple example of kernel applied over a entire image. We can apply a kernel from the beginning of the pixel to end of every pixel also. So in such case, we may consider okay, 10, 20, 30, 40, 50, 60, 70, 80, 90. So if I want to apply to only this part means I can also apply the kernel. Okay. So this is the basic convolution operation and there are some properties are there. The convolution operation or the linear filtering can be of commutative, associative and shift invariant. Commutative means the order doesn't matter, which means we can blur and then sharpen or sharpen then blur. Both produces the same images. Okay, and both should be applied with a linear filter. Associative means it can combine filters before applying, which means we can blur with kernel 1 and then blur again with kernel 2. This is same as that of making a single bigger kernel. So k1 into k2, instead of applying it two times we can apply it in one time. Okay, then shift invariant, it works the same everywhere in the image. A blur applied on the top left corner, it will work exactly same as the bottom right corner. So all the images will be look same. If you shift the input image, the output is shift the same way. The next one is padding. So it will be needed at the edges when the kernel goes out of bound. So consider this example, we have applied the kernel in every image. So if I want to apply a kernel in the pixel 90, but the kernel size is 3 cross 3. So image pixel I am going to focus on 90 means my kernel goes out of bound. My image pixel is 10, 20, 30, 40, 50, 60, 70, 80, 90. So this is not the original image pixel. I'm just taking as an example. So if I want to apply a filtering in this 90 means I have to apply the kernel this in this way, but my kernel size is 3 cross 3, so I have to use 3 cross 3 values, so I may consider zeros. So this is known as a zero padding. This concept is known as zero padding. Whenever the kernel goes out of the bound, I can use the padding concept. So it will be needed at the edges when the kernel goes out of bound. Zero padding means all the edges will be darkened. So we know the color value ranges from 0 to 255. 255 represents white and 1 represents, 0 represents black, mid of 0 to 255 represents gray. So if we add 0 means all the edges of the image will be darkened. So I'm going to take the original images 10, 20, 30, 40, 50, 60, 70, 80, 90. Zero padding means all the corners are applied with the 0, which means all the corners are applied as a black color. So the clamp second type of padding is clamp replication. It will extend the border pixel inward. See the example here. So 10 means all the corners will be represented as 10. 30 means all the corners will be represented as 30. About 20 it will be 20. So in case of 70, all the corners will be represented as 70. All the corners are represented as 90. Mid value considered as a same. This is known as clamp. The next one is mirror. It will reflect the pixel value at the edges. Okay, so we know this 10, 20, 30, 40, 50, 60 and 70, 80, 90. So this is the original matrix, original image pixel we know. Okay, so we have to first mirror the first two rows. So first mirroring represents this value. Okay, so this is okay. Then 40, 50, 60, 70, 80, 90, we have to mirror this. So again this value comes down, 40, 50, 60. So this is known as horizontal mirroring. Next we have to perform vertical mirroring also. Consider this vertical mirroring for 10 will be 20. For 40 it will be 50. For again 40 it will be 50. For 70 it will be 80. For 40 it is 50. So in this case consider the vertical mirroring. For 60 it will be 50, 30, 20, 60, 50, 90, 80, 60 and 50. So this is known as mirror padding. We can apply any of this padding technique and we can apply the kernel in the edge pixels. Next one is separable filtering. I have shown an example here, right? So this example is a consider this example for non-separable filtering. So you can check the number of operations here. Multiplication has done 1, 2, 3, 4, 5, 6, 7, 8, 9. We have done 9 multiplication and 1, 2, 3, 4, 5, 6, 7, 8, 8 additions. So it is just a non-separable filtering. When we apply for separable filtering, some kernels can be split into horizontal paths and some can be considered as a vertical paths. So one of the most famous example used for separable filtering is Gaussian filtering. So we will have we will have only 2k multiplication instead of having k square multiplication. So let us see an example for separable filtering. I am going to consider the same matrix. Okay, so the kernel is divided into two, horizontal kernel as well as vertical kernel. So horizontal kernel, I am going to take 1, 1, 1, which is nothing but 1 cross 3, and for vertical kernel, I am going to do 1, 1, 1, 3 cross 1. So the kernel may vary. For simplicity, I have taken as 1, 1, 1. Okay. Give me a minute. Yes, we have seen an example for separable filter, right? For space, I have removed all the content which I have already written. So let us write once again. So I am going to take an image 10, 20, 30, 40, 50, 60, 70, 80 and 90. I am going to use a horizontal kernel 111, and I'm going to use a vertical kernel 111. So if I want to perform the filtering in the pixel 50, so let us take the horizontal kernel. So the horizontal kernel 3 cross, oh sorry, 1 cross 3. So I'm going to take only this place 40 into 1 plus 50 into 1 plus 60 into 1 will be considered. Okay, so here it results in 150. So then on applying vertical filtering, I focus only on 20, 50 and 80. So here you can see that I have applied the filtering only for the 50. So similarly for 10, it will take the horizontal filtering. So it may be padded with 0 or clamp or mirror, whatever may be, based on this value every pixels will be uh, horizontal kernel will be applied. Okay, so in this case, for 20 it may be 10 into 1 plus 20 into 1 plus 30 into 1. So 10 plus 20 plus 30, the result would be 60 here. On applying 50, we got 150. So for 80, we'd have some other values, right? So 70 into 1 plus 80 into 1 plus 90 into 1. So 70 plus 80 plus 90 would have got around 240. Okay, so 240. So on considering this vertical filter, we'll take only the scaled values. So not scaled or the filtered values. 60, 150 and 240 will be considered. So what we have seen is for considering 50, the horizontal kernel applied the result 150, and applying the same for vertical, we will not get the previous value. The horizontal filtered value will be considered. So the result would be 60 into the same vertical kernel is applied 60 into 1 plus 150 into 1 plus and 240 into 1 will be considered. So based on this, we'll have some result. Okay, so now you see on applying filter for the value 50, on horizontal kernel produced 3 multiplications and vertical kernel produced 3 multiplications. In previous example, we have seen totally 9 multiplications for each pixel. So the result is reduced to 9 to 3. So 3 square is converted to 2k, 2 into 3. Okay, so 9 is reduced to 6. That was mentioned in the separable filter formula. See here. So a k square multiplications is reduced to 2k multiplications. So it performs the filtering in fast manner. Example of some other linear filters are box filter. The box filter is the one we have seen for the convolution example, right? So it is a square window. It will apply values on every pixels. At the end, it will be averaged. Then the tenth or barlet filter. So you can see the result is a tenth. Okay, so 100 2. The edges will be lower and the mid value will be higher. So similarly, 2 4 2 1 2 1. So it is similar to a tenth. Gaussian filter is similar to a curvy one. So the edges are sharp here, but in case of Gaussian filter, it will be like a smooth curve. Okay, 1 4 6 4 1. You won't get any sharp edges. We'll get a blended one, so it will produce a smooth or look like a natural blur, and it is good for noise reduction. So the next one is unsharp masking. Oh, so the definition is sharpening an image by subtracting the blurred version of it from the original. Okay, we'll sharpen image using this unsharp masking. Let us see an example. The original image is 40, 50, 60, 50, 60, 70 and 60, 70, 80. So what I'm going to do is I'm going to blur. So the blurred pixel from the original pixel is represented here. How we are going to blur means we are going to take a neighborhood average. For 60 means take all the neighborhood values and perform the average. Okay, so for 40 means 50, 60, 50 and average divided by 3 will get this value. So this is the blurred pixel of the original image. The next step is, as per the definition, we are going to subtract the blurred version of it from the original. So we are going to subtract the blurred version from the original. So 40 minus 50, 50 minus 55, 60 minus 60. So similarly, performing for all the rows, we got a subtracted the blurred from the original matrix minus 10 minus 5 0. So this result will be added back to the original result 40 50 60 50 60 70 60 70 80. This produces the new matrix 30 45 60 45 60 75 60, 75, 90. So you could see the change from the original value. So this is the result of the sharpened image. When you apply any filter like sharpening, so this operation would be happen. This is one of the operation we can use to sharpen our images. So the next one is Sobel operator. Sobel operator is mainly used to enhance the vertical edges as well as the horizontal edges. If you want to enhance the edges of the images, we can use the Sobel operator. Similar kind of mathematical operation will be goes inside a Sobel operator. The Sobel kernel will be applied to each pixel of the images, so it will result in the edge brightening. So the next one is band pass filter and steerable filter. So band pass filter means, so low frequency, high frequency will be removed. Only the mid frequency will be considered. So the Laplacian of Gaussian is also used to detect the edges and blobs. Steerable filter means the filters can be rotated. So we have seen a 3 cross 3 matrix, right? So kernel matrix, this can be rotated to some 30 degree or 45 degree to produce a new matrix, and those matrix can be again applied to the image pixel to get a result. Okay, the next one is summed area table. Okay, so in summed area table, will pre-compute cumulative sums of pixels for fast box filtering. Okay, see this example here. The original matrix is given here 1 to 16. The summed area. The summed area is 1 plus 3, 1, 3, 6, 10. How this is obtained means, so look at this 2. Before that we have only one value, so 2 plus 1 will be 3. Consider this 3 will not check the 2, will check the summed value. So 3 plus 3 would be 6. For 4, already previous value is 6, so 6 plus 4 would be 10. So in this case of 5, check the previous one. The previous one is 5 plus previous one is 6. 5 plus previous one is 6. When comes here, we have to check very carefully. The current value is 6. The previous values are 6 and 3. So add both the values 6 plus 3 and we'll get the result as 9. And consider this value also. 9 plus 6, it is 14. For 7, consider the previous two values. 14 plus 6, so the result would be 20. 20 plus 7, 27. We have to subtract this value, so this results in 24. Okay, similarly this also 9 plus 6 is 15. We have to subtract with value 1, so that is 14. So here consider this point 8. The previous two values are 24 plus 10. The current value is 8. So what do we get? 34 plus 8. 34 plus 8 would be 42, right? 42. 42 minus the previous top left value is 6, so we'll get 36. So that is what the summed area will be obtained. So the formula is, we have to add all the values s I minus 1 I minus 1j, s I comma j minus 1, and we have to add the ij. Finally we have to subtract with the I minus 1 and j minus 1. Okay, consider this as ij. We have to add I minus 1j as well as I comma j minus 1 and the current ij. Finally we have to subtract with I minus 1 and j minus 1. This is the result of summed area table. The last is recursive filtering. IAR filter and FIR filter is there. It represents infinite response, it represents finite response. Here the output depends on the previous output. Here the output is depends only on the current input pixels. So these are different types of linear filtering we can use according to our application. Thank you.